Okay, welcome to AP Review 8 Solutions. We have two problems involving collisions and energy. So we'll take both in turn, mostly derivation type stuff and a little bit of graphing, a little less of the um, paragraph writing, but it's the same idea at least. We're not worried about calculations. Okay, so we have two balls falling together, a small mass on top of a larger mass. This is actually a kind of cool demonstration. You can find one on YouTube, or especially with like a bouncy ball, with the idea that after the colliding with the floor, the larger ball then collides with you, if you will, with the smaller ball and sends it up to a very large height, a much higher height than they started, and it's still within the law conservation laws. Okay, so we just have to do a bunch of derivations. So the first one is find the speed of the large ball just before it strikes the floor after it falls a distance h, and that's pretty straightforward. You can do that either kinematics or conservation of energy. I'm just going to do conservation of energy. In fact, you can look at the rubric for it, but basically UG is show, basically always put it in terms of conservation as a change. So the loss in one equals a gain in the other. You substitute in 3mgh, you substitute in 1/2 3mv squared, and the final velocity vb, which they want, is nothing more than a radical 2gh, as we should expect. All right, we see that a lot. All right, we're going to use that. Now we want to talk about the ball comes up and then hits the little one on the way up. So the big one is moving this way while the little one is still moving VB. And you can see them labeled right there. And they want an equation in terms of their initial speeds before the collision with each other, not the floor. So this is after the floor collision. And then their speeds after in terms of VS and VL, S being small and L being large. Okay, so that's a collision. They're not sticking together. It's a straightforward and basically make a statement, right? Sigma p equals sigma p prime. So what is the initial total momentum? Well, it's the momentum of the big ball and a small ball. So I'm going to just jump right into that. That's 3m vb, right? The velocity of it coming after, plus m. Now here's where we're going to be careful. They're going in opposite directions, so we got to call one of them negative. I'm going to just call this one negative. Doesn't matter which one you call negative, okay? But you must make sure you do that. And then that's going to equal, 3m VL for the velocity of the large, and then plus m of the times Vs. The m's all cancel out, right? Because we're all in terms of each other. Okay, so we basically get, if I simplify the left term, I get 2VB equals 3VL plus VS. All right, and you'll see that solution there. And again, we expect that they'll be going in the same direction after the collision. All right, so derive that, and then if we scroll down, we move on to see, we say after the collision, VL is 0. So in other words, the large ball comes to a stop upon hitting the small ball. So use your relationship that you found in the previous one. Determine the speed of the small sphere in terms of VB. Okay, so that should be pretty straightforward. We had 2VB equals 3VL plus VS. So VL is 0, so that's just going to be VS. So that's just going to be twice. So the small ball is going to go off with twice the speed as the large ball came off after it hit the floor. All right, now we want to find out, is this elastic or not? This is the part that's most involved mathematically. So again, elastic means was kinetic energy conserved? And this is, again, got to make sure we identify what aspect we're talking about, the collision between the big ball and the little ball after the big ball has hit the floor and bounced up. Okay, so that's going to require a bit of math. So let me do that on a blank sheet. All right, so let's take, like we said, sigma k e All right, that's the kinetic energy of both of them before they collide. Remember, they were both moving with a speed of VB. The negative isn't going to matter because we're going to square it, so that's basically 1/2 3m times VB squared plus 1/2 m times VB squared. Now technically it's negative. I'll throw a negative in there just to be thorough, but that's fine. So we have, let's see, 3/2 mVB squared plus 1/2 mVB squared. So 3/2 and a half is 2 mVB squared. All right, so there's the before. Now let's see what happens after. So sigma KE after. We were told that VL, right, that's what afterwards, that was 0, so that term is going to be 0, so that just leaves us with 1/2 m. And we found that it was moving with the speed of 2 VB afterwards squared. So that's 4 mVB squared times a half, which is 2 mVB squared. And they are the same, so we can say this is a perfectly elastic collision. Okay. Last problem, last part, determine the height that the small ball rises. Okay, so that's really another conservation of energy. We can make the statement that the loss in kinetic energy of the small ball, right, as it rises equals the gain in potential energy, gravitational potential, whoops, I shouldn't put an S there, of the small ball. Okay, so we take that kinetic energy, which we found, well, let's just do it right here. We have it right there. So it's going to lose 2 mVB squared, and that's going to go into mgh prime. Okay, m's cancel out. Okay, so we see h prime equals 2vb squared all over g, and then we got to substitute in what we found in part A. How fast is VB, right? So if we go back to part A, so we have 2, and that was radical 2g times the original h squared. It's going to be the square root of that, so if we square it, we get 2gh all over, right, g. G's cancel out, and we get 4 times the original height, and that's what I said to expect when we have that situation. Okay. So let's move on to the next problem. Sorry, I'm having a hard time scrolling. There we go. Okay, so we have a plunger pushing on a block, and they want you to graph it as a function of time, and then they do it for a marble. And the key thing here, we want to read this, is we have frictionless, so we have contact from A to B, no friction from B to C, friction from C to D, no friction from D to E, and then a collision, an inelastic collision from at point E. And a very important aspect of this, if you read carefully, is that we're looking at the center of mass of the system. That's what we're going to plot. Okay, so let's make sure we understand. The center of mass of the system before anything is done is right here, but that's not critical. You don't have to put position on there. But what you want to understand is that if our system is the both blocks, then the only force acting on the system is when the plunger is pushing it and when friction is acting on it. So if we, in other words, all we have to really worry about is what's going on with this in terms of its motion until the collision, and then we'll revisit that. So again, the center of mass only changes if there's an external force. If our system is defined as both masses, the only external force comes from either the plunger or the friction here from the ground. The fact that the two sits there doesn't really matter for how our center of mass changes. And that will make the problem a whole lot easier when you go to do it. Okay, so if it's really just basically how block 1 behaves until it hits block 2, then this should be pretty straightforward. So initially, it's not moving. Okay, and then it's going to go to it's going to increase speed steadily because it's a steady force. I believe they make that clear. It's a steady force. All right, so I'm going to choose some arbitrary point, and the speed should go up in a straight line. Then from B to C, it's no longer in contact. It's a frictionless surface, so it's going to be flat. First law of motion. All right, then it hits the friction, so it's going to slow down. We're assuming the friction is a constant friction, so a constant acceleration. So a constant slowing down. So I'll choose some arbitrary drop at a lower one, and then from D to E, it's going to go at a steady speed again. Okay, now the collision occurs here. And they stick together. It's very tempting to say that it's going to slow down further because we've learned that when both blocks, when things stick together, they slow down, which is true. But remember, we're talking about the center of mass and how it behaves for the system. So is the collision an internal or external force? Well, that's an internal force. So if it's an internal force, then there can be no change in the motion of the center of mass. So in other words, it keeps going steadily. All right, so it's very easy to drop that down. That would lose you a point. Wouldn't be fatal, but again, it's a simple mistake to make. All right, in the next situation, we are pushing on a ball. Again, it's frictionless, friction, no more blocks. We are, if you read carefully, they put this little, I don't know, addition to it so that it's pushing on the center of mass, and that's actually pretty important. Okay, and they want you to plot or how the angular momentum changes, I believe, as a function of time. Oops, I went too far. Whoops, sorry, I did the wrong graph, didn't I? Wait. No, I didn't. Okay, I'm sorry. We don't make a graph, we just explain. Okay, I'm sorry. So, let me go back up to the plunger then. And I'll explain it here. It's very tempting to, okay, so initially it has no angular momentum, and if it's going to get angular momentum, it's got to roll. So from A to B, if it's going to start rolling, if it's going to gain angular momentum when it didn't have one, there has to be an external torque. And that's the easiest way to look at this. So where would the external torque come from? It could come from one of two places because there's essentially two forces acting on it. There is the applied force this way, and then there is no friction. So there can't be any torque coming from friction because there is none. And since this applied force acts to the center of mass, there is no external torque there. So in other words, there's going to be no gain on angular momentum. In other words, it's going to slide across here, and it will steadily slide until it hits CD. When the marble hits CD, now there is a force, friction, that's acting off its center of mass, so that's an external torque, and it will gain angular momentum from C to D. And then from D to E, it no longer has that friction, so it just keeps rolling as it was before. There's going to be no change, even though there's a transition from force or friction to no friction. So the only time that you're going to have a change in angular momentum is when there is that external torque. Okay. As always, if you have questions, make sure you ask, and we should be good.